Okay, so yeah, where do you want to start today?
Um, I will say I didn't get through all of the physics chapter just because a majority of that stuff was new to me
Yeah,
because it
no,
just
that's
was
fine.
not covered at all.
Hmm.
So I got up to I have it written down. Um,
Okay.
I got up to 6.2.
Okay.
Um, but I didn't really I was just like kind of I didn't it's like 6.2 I have to reread because I was just really just skimming through it.
Okay.
But other than that, I took really I think I get it for the most part, but I do have questions.
Okay. Cool. All right, and that was the circuit chapter 6.2, and so you got through the more important chapter here is 5 anyway. So
Okay,
for
cool.
the physics stuff, but and the gen chem I would say is generally slightly more important than the physics for this, but we can start wherever. So
Oh, no. I want to start with the chemistry because that's where I had
oh,
the most
okay, okay.
questions. I was just letting
Oh,
you
okay.
know that I didn't get through the all of the physics chapter.
Oh, gotcha. Okay, cool. Yeah. So yeah, where do you want to jump in?
Okay. Um, this is like a stupid question, but I just couldn't my brain wasn't really like just wasn't clicking and then Google wasn't making sense to me when I tried Googling it. So
Hmm.
is like you know how like you have like different types of reactions like double replacements like the list of reactions
Yeah.
is solvation a reaction type?
Mm, I know what you're saying. No, I'm trying to think of what you're saying. Um,
Oh.
Salvation is weird because it's not like there aren't any covalent bonds being made or broken
Mm,
in a salvation reaction, but you are sort of breaking ionic bonds. So it's more of like a change in the intermolecular forces. Generally speaking, salvation reactions are just pretty dramatic increases in entropy. Because you
okay.
go from having like this really organized crystalline solid to and so you've got like a heterogeneous situation versus then it becomes homogeneous. So you're just like spreading out
Yeah.
stuff.
Okay,
Yeah.
that's what I was thinking, but I was like, what? Google says it is a reaction, but it doesn't
Yeah.
really. Yeah, okay.
And it doesn't really matter, honestly. Like they're never going to ask you whether it's like quote unquote a reaction or not, because that is kind of just like an arbitrary man-made definition. You know what I'm saying?
Okay.
So they
Yeah.
care more about principles and ideas rather than like stupid definitions of stuff.
And then okay, next question is excuse me, sorry.
Oh, you're good.
Um, the Kaplan textbook listed out some common solutes and common solvents. Are those worth memorizing?
Where was that
It
specifically?
was at the very beginning of the chapter, but I wrote them down, and the common solutes are NaCl, NH3, C6H12O6, and CO2. And then
Okay.
the common solvents are H2O, benzene, and ethanol.
Yeah, they're worth knowing. I would say it's worth
Okay.
knowing. Yeah.
Okay, cool. And then,
You can generally predict like how all of that stuff is how all of the solvents are going to behave just by noting whether they have hydrogen bonds or not, like what the different intermolecular forces are
okay.
in the solvent itself. Right,
Okay,
like
cool.
H2O has a ton of hydrogen bonds, right? And CHO or CH3OH or CH2, CH or whatever, ethanol, methanol, all of those, they also form
Yeah.
hydrogen bonds versus benzene isn't. And so it's more of like an inorganic solvent. That's the important stuff to know on that. Um,
Okay, cool.
and as far as the solids or the solutes go, if you see the on the page where it says the solubility rules, it's got like 7 rules listed out.
Yeah, I got those
That
written
is
down.
memorize those. Yeah, those you absolutely have to memorize.
Okay, cool. Because Kaplan noted that it was like you have to know rule one and two
Yeah.
with um um like with the exceptions of PB2 plus and I can't read what I wrote. Oh, AG plus, you know.
Uh-huh.
But is it so you would recommend memorizing just all of them?
Yeah, I would say just memorize all of them. 1 and 2 are the most important, but knowing all of them you're gonna have to know all of them, I think, personally. Like
Okay.
if you want to not do as well and memorize less of them, but yeah, I think that you have the ability to do really well, so might as well memorize all of them. Like
Okay,
as
cool.
you aspire to doing better and better on this test, there's more and more you just need to know. So yeah.
Okay, cool. And then the next thing of it was like I titled it factors of like the reaction spontaneity.
Hmm.
And the question I had is like if I don't know if this would ever be asked on the MCAT, but if we're faced with like both changes in enthalpy and entropy, which one weighs greater in the spontaneity of a like a of a solvation reaction?
I'm sorry. Could you restate that? I'm so sorry. I was just Casey just sent me a text saying somebody broke into her car, and so I was just like, "What the
Uh,
hell?"
no,
But
that
it just
seems
like
pretty
popped up on my
important.
other screen. Sorry about
No, that seems pretty important. I hope
that.
Dr. Casey's okay.
Yeah, I think she's fine. She's probably just she's this sucks because she's super paranoid about everything anyways. I'm like, damn it. Sorry, go.
Uh,
Yeah, could you just restate that?
Yeah,
That's totally my
so
fault.
like when you're talking about like reaction spontaneity with
Mhm.
dissolution and stuff like that,
Yeah,
if we're ever faced with like both if like they're like, hey, there's both changes in the enthalpy and changes in the entropy, how do you
yeah.
determine which one's a greater like proportion to the spontaneity?
The just this equation, delta G equals delta H minus T delta S.
Okay.
So you just calculate delta G, and so whichever one, like, so temperature is what matters, right? If they don't agree,
Yeah.
like it, because you could have, here I can just make like a quick table. So if you're gonna have a delta H and a delta S for every reaction, right? And so you could
Yeah.
say you can have various scenarios where we'll say just like scenario one, you've got delta H is we'll say delta H is negative and delta S is positive, right?
Mm.
So in that case, they agree, like they both want to make delta G negative and
Yeah, they
everything,
want to make
right?
it lower.
Right, right. So that's not a big deal. The same goes for this. That's also not a big deal because again, they agree in the direction they want to move delta G, right?
Yeah.
But in the
Okay.
cases where they have the same sign, these are the ones where you need to know that, it just depends. And well, it depends. What it depends on is temperature.
Okay.
So yeah, so when temperature is high, delta S wins out. When temperature is low, delta H wins out. And that's always the
Okay.
case. Yeah.
Okay. Thank you.
And the reason for that is because temperature, and I think I mentioned this the other day briefly, but temperature is average kinetic energy of the molecules in the sample, right? Or
Yeah.
in the substance. And
Yeah.
so the change in entropy matters more because the total number of possible configurations the system can take on matters more if you have higher kinetic energy of your particles in the system, because that means that you're going to have more of those possible configurations actually take place.
Okay.
Because the,
Okay. Yeah.
the particles are
Yeah.
moving around more
Yeah.
versus if
Yeah.
the particles aren't moving, then it doesn't matter how many configurations you have because you're not going to use them all.
Okay. And then I'm sorry, I have a list of questions for this chapter.
Mm. No, that's really good. Like that gives us stuff to talk about that we know for sure is going to help you. So that's helpful.
Okay, cool. And then like one of the like key objectives of the chapter was to describe the process of like um salvation, right?
Hmm.
And like I understand that when you put like a solute in a solvent, the intermolecular forces are like rearranging and stuff like that. But is it just because you're just dropping in the solute that they start to do that because those intermolecular forces start to interact?
Versus what?
Like
Like,
that's what I'm I don't know if I'm
okay.
asking this right. Like uh I don't know, it's just more of like is that the reason why it starts to is because those intermolecular forces start interacting the second you start putting the solute in.
Yeah, that's true.
Okay.
Yeah. And so if something isn't going to be soluble, if the forces between the things in the solute, like between the Na and the Cl, for instance, are greater than the forces of the solvent with the individual parts of the solute. So
Okay.
something's only soluble if the solute solvent reaction plus the increase in entropy you get is more favorable than the solute solute interaction.
Okay. Cool. Thank you.
And that's kind of a
Um
complicated statement, but that's about as
it,
simple as
it
I
made
can make
sense.
it.
It made
Okay,
sense.
cool. Good, good, good.
Um and then I need to go back. I just wrote a note to go ask something about the last paragraph of the solubility thing, but I
Okay.
didn't write it a page number, so let me see if I can find it really, really quick.
And you mean like the last paragraph of the chapter?
I think so.
Okay. Yeah, I'm going to it also.
Introduction.
This is the part talking about osmotic pressure.
No, let me read.
Okay.
I highlighted this all, like, and then it just didn't save any of my highlights.
Oh, that sucks.
Yeah.
What'd you use to highlight it?
You know how you can open up the Kaplan thing and then you can click, I use Microsoft Edge because it's just quicker than any
Yeah,
other
yeah, that's
browser.
true. Yeah.
Um, and they have a highlight feature when you open PDFs, but I don't know
Oh,
why
that's
it
really
didn't
cool.
save.
Maybe I should use Edge. Damn it, then I'm gonna have to change all my stuff to Microsoft.
Edge, I like Edge. It's the quickest. It doesn't have the best compatibility with things.
Oh yeah, yeah. I just use Chrome for everything. Just I think it doesn't matter as long as you keep using this. I'm just gonna keep using Chrome. Uh,
Uh, I can't find it, so if I see it again, I'll I'll find it.
okay, cool.
Um, and then one thing I really wanted to note on that we were talking about last time is like how we at the very end we were all talking about like when things start connecting together.
Yeah.
Well, we started I've never learned about ligands before, and I
Oh
was like,
yeah.
"Wait, this connects to my cellular neuroscience class." And it was like it was that like moment of like, "Oh, I understand what's going on."
Oh nice. Yeah. Yeah, that's gonna happen a lot as you prepare for this test over the course of the coming months, for sure.
Okay. And then where's my other questions? And then I didn't really the way the Kaplan book was explaining it, I didn't really understand how normativity factored into solutions. I
Oh, that's a
just
good yeah.
yeah.
That's what you're saying. So on so you know what the do you know what the Van Hoff factor is? Do you remember what that is?
Yeah. So for like
The I
organic
thing?
compounds, it's 1, and then you have to calculate how much it's gonna dissociate after you do the dissociation, like,
Yeah,
equation.
yeah, and so it's like how many things go it can will end up in solution as it dissociates, right? So the normativity is kind of like that, but not exactly. So what normativity means is, well, it's kind of like your thing that you're concerned about. So for instance, if you're worried about like an acid-base reaction, then
Mhm.
the normativity is how many units of acid or how many units of protons you get out of 1 mole of acid, right? And so most acids will be one, will just have a normativity of just one, right? So like
Yeah.
for instance, HCl, if you have HCl plus water, then obviously like that reacts to form H3O plus Cl minus, right?
Mhm.
And so you know that 1 mole of HCl is going to give you 1 mole of H3O plus, right?
Okay.
But like sulfuric acid, H2SO4 plus water will give you again one H3O plus, but then you've got HSO4 minus, right? And that HSO4 minus can go on to, it reacts with water again to form another H3O plus H3O plus SO4 2 minus. And so now this one H2SO4 has given you 2 H3O pluses. And so for that reason, H2SO4 equals 2 normal. So 1 mole of H, so it's like
Oh,
how
it
many equivalents you get out of it.
okay, that makes so much more sense now. I just when I just when you're reading things and it just doesn't make sense when you're reading it in your head.
Yeah, yeah, no, I totally understand for sure.
Okay, and then on page 3713, I had a question.
Okay, what page? Let me open it up. I don't have the thing open right now.
I have it up. I can share the screens if you want.
Okay. Um, Yeah, might as well. Go ahead. Let
Okay.
me I think I do I have to stop? I think I have to and I'll try to open it
Present
also.
uh window this one. Um I just I didn't like I read the solution and everything, but I just don't understand what the question is asking, right? Because
Okay.
it's saying the molar solubility of FeOH3, right, is an aqueous solution. In an aqueous solution was determined to be, 4 e to the negative 11. What is the value
Okay.
of KSP? at the same temperature, right?
Yeah, yeah,
But in molar solubility, it's at equilibrium. That's what it says up here. Molar
okay,
solubility is when the solution is saturated,
yeah.
and when the solution's saturated, it's at equilibrium. So I don't understand why it's not the KSP is not 4e to the negative 10.
Yeah, I got you. Okay, this is a good question. This is a really good question. All right, so it's a molar. I'm writing it down really quick, and then I'll start sharing my screen again just to show
Okay.
you what I'm doing. Okay, so molar solubility it said was four times 10 to the negative 10,
Hmm.
and it said moles per liter.
Yes.
Okay, and it's asking, and the question is just like, what is the KSP, right?
Yeah. What is the value for the KSP?
Okay, yeah. So what is KSP? And it's saying of it. It said of iron 3 hydroxide, right?
Yes.
Okay. All right. Cool. Okay, cool. Yeah, so I'll go ahead and share my screen again now. Let's see. Okay, so yeah, so first thing we have to do here is define what molar solubility is, right? Because I think that that's you can't get this without knowing what that is. I think that might be your issue. So let's figure out what the difference is between KSP and molar solubility. Okay,
Yeah.
so molar solubility is just telling you. I'll just write it out like this: molar solubility. It just
Is
tells
the
you.
molarity of the solute in the saturated solution, right?
Yeah, it's like the maximum number of moles of solute that can go into one, just say 1 liter of solvent. So that's what molar solubility is. Versus KSP is not molar. KSP and molar solubility are two different things. KSP is KSP equals KEQ for a solvation reaction.
Mm.
Okay. All right. So let's write out so we have to write out the problem, right? And so the problem is iron 3 hydroxide, FeOH3 plus water. And that's going to exist at some equilibrium where you've got Fe3 plus, right? And so this is a solid here, right? And water
Mm.
is a liquid. So you've got Fe3 plus aqueous, because now it's gone into solution, plus 3OH minus, and that's also aqueous. And then you've still obviously got your H2O liquid, and there we go. Okay. So, all right. So KSP is just the KEQ for this specific reaction,
Mm.
right? So if we say what is the KEQ? All right. Well, KEQ, KSP, same thing. So what would the KEQ be for this reaction?
It would be bracket
Mm-hmm.
iron cation, the 3 plus, and then bracket OH minus 3.
Okay. Yeah. And that's raised to the power 3, right?
Yes.
Okay. Yeah. And so what about in the denominator?
Uh,
Because it's just products divided by reactants, right?
yeah.
But there's nothing in the
There's
denominator
nothing in the
here.
denominator because it's a solid and a liquid.
Right. Yeah, exactly. Perfect. Yeah,
Okay.
so that's all it is. So the reason that we even have a KSP is just to say, hey, this is a solubility problem. But it's literally the same exact thing as KEQ. And so you know that the units are going to be totally different than they are for molar solubility, right? Because molar solubility is in moles per liters,
Mm.
whereas this is just in what, like, moles squared or whatever. You don't really think about units of equilibrium constants. So this
Yeah.
is just an equilibrium constant. And so there's going to be a difference here because they're just two totally different things.
Okay.
Okay. So the question then is, how can we calculate KSP given molar solubility? All
Yeah.
right. Okay. So we know that this molar solubility right here, that's telling us how many moles of this will go into 1 liter.
Yeah.
Okay. So how can we use that to calculate KSP? Well, to calculate KSP, we need to know how many moles of iron are in solution and how many moles of hydroxide are in solution, right?
Yeah. And
Okay.
that's where the equation comes in.
Which equation?
The written out dissociation equation, because then you can look at the
Okay,
coefficients.
perfect. Yeah, exactly. So what do
Okay,
you do?
I so then it would put equal sign. There's 1 mole of iron,
Okay,
a-
right.
and then I guess X.
Okay, yeah, yeah, yeah. So you could say, yeah, X is equal to Fe, or yeah, X is just equal to like how many moles of this are in solution, right?
Yeah,
All right. So that's the same thing as how many moles of this are in solution.
yeah,
Okay. Yeah. And so that's that X value is going to be your 4 times 10 to the negative 10, right?
yeah,
Okay. So yeah. So you got over here, you could say 4 times 10, or actually, we'll just keep X there. Screw that. All right. So you got X, one of them. All right. So then what about the OH?
you would have that cubed, the X cubed.
This X, or put another X?
Uh, Another X.
Okay. And cube it.
Yes.
There's one thing you're missing though.
I'm missing um the 3 in front of the X.
Right. Yeah, exactly. Yeah. So then you have 3x cubed. Right.
Yeah.
Okay. So then just simplify it before we put the numbers in, just to make our lives easy. So what does that simplify out to?
Uh Math. uh Holy cow, I'm drawing a blank. Wow. I actually forgot my exponent rules just now.
Oh, you're good. No, well, most people will just blow right through this though and say like a lot of people will just say 3x to the 4.
Yeah.
And that's not right though, because this is a 3x cubed, right?
Yeah.
So what is
Oh,
3x times 3x times 3x?
um whatever 27 times 3 is. I can't do math in my head today.
Oh, you don't need 27 times 3, right? Because it's just 3 times 3 times 3. So it's just
Oh.
27. Yeah.
Yeah, okay.
Yeah.
You can tell it's been a long day.
Oh, you're good. No, you're fine. I mean, everybody misses that. So you actually, I would say, would get this right because you were aware that it was more complicated than that. So then you end up with x times 27 x cubed, right? And x times
Mhm.
27 x cubed is just 27x to the
X to
4,
the
right?
4th. Yeah,
Yeah.
and then you would plug
So
in
then
X.
you just plug, yeah, you just plug that in. So you've got 27 times 4, but that 4, right? So 4 times 10 to the negative 10, and that is raised to the power 4.
Yeah.
All right. Well, that's a pain in the ass. But all right, what's 4 times 4 times 4 times 4?
16 squared.
Yeah, which is 256.
Yeah.
But, like it's not even that important because of the exponent. But yeah, 256 times 10 to the negative 40.
Yeah.
Okay. Yeah. So your answer is somewhere like something like that.
Okay, cool. Thank you.
And you can simplify it more too. 27 times 256. Well, I mean, like that's a lot.
Yeah. Okay. Okay, yeah, that actually I just was confusing the definitions of molar solubility and KSP.
Oh yeah, yeah. No, you're fine.
Okay.
But that's like your classical solubility problem. Like that
Yeah.
that is something you absolutely need to know how to do. How to, like use the sub the X in as molar solubility and figure it out that way. That's so
Okay.
that's why I was saying that's a really good question. We were gonna do that problem today regardless.
Okay.
So yeah, that was on my agenda.
Awesome. And then I have one more question. Um I don't know, but like in the textbook, I don't know if this is like a mishap of like oh, never mind. I had misread this sentence and it just wasn't making sense, but I get it now. After
Oh,
like
okay.
I'm gonna ask you about it. I thought they were all just like repeated, like copied and pasted, but I didn't see the subscripts on the X where it says like it's saying key concept, so I get it now.
Oh, okay. Cool.
It was just a mishap.
Yeah, no, I see what you're saying.
Okay, cool. And then, did I have any more chemistry notes or questions? No. Okay. I don't have any more chemistry questions.
Okay. So are you good on all the acid-base stuff?
Yeah, I was pretty good reading through that.
Okay. All right. We may come back to some of the acid-base stuff after we answer your physics questions.
Okay.
If that's cool.
Um, let's see. Um, the only one I had a question on so far in the physics was equipotential lines.
Okay.
Um, I don't understand how it's the potential's the same at every point.
Yeah. Will you tell me what page that's on? I just want to see specifically what you're looking at.
I didn't write this page down.
Oh,
This
okay. Dang.
I got it. I can pull it up.
I'm just trying
Physics.
to remember what their picture looks like exactly on the
Oh, I have it
equipotential
drawn.
side.
I can share my
Oh, okay.
screens.
Okay. Yeah. Yeah. If you don't mind.
Cool. Can
Oh,
you?
you're saying in the special cases of electrostatics thing?
Yeah.
Yeah, that problem's a pain in the ass. That one that is truly a very annoying thing to think through. Let me get to that page. Okay, there we go. All right, yeah. So it's just saying that, well, like equipotential lines, are just simply saying that like the electric potential is equivalent at each space at each spot here,
Hmm.
and so it's just saying that like with reference to the two charges at various distances, we have the same potential because it's being affected different at different levels by the two different charges as we move to these different distances. And so it's just the same electric potential at those spots. Yeah, I think that maybe explaining or discussing what electric potential is might help a lot with
Okay.
that question. So what's your definition of electric potential? Because that's something that's really hard for people.
Um, I just don't want to. I don't want to repeat what I wrote down.
Oh, you can go for it.
Uh, I wrote down work necessary to move a test charge away. Uh, can't read what if I wrote something infinity to a point in a space in a electric field.
That's fair. Yeah, that's a good definition. You can also think of it as just the work necessary to move a charge from point A to point B. Too, like if you know the potential at A and you know the potential at B, then the
Mm.
electric potential different. That's the difference. But because the from infinity to there says like what that potential is in a vacuum. Without
Yeah.
needing the situation. Because so what are the units of electric potential?
Ooh. Is this the one I forgot to write them down? I did.
All right.
Uh, I know the equation.
Okay, yeah, what's the equation? Go ahead.
Delta U is equal to K, big Q, little q over R.
Okay, hang on one second. Sorry. Electric potential is what?
Uh, K times big Q times little q over R.
Okay. Yeah, K times P Q times little q over R. All right. Yeah, so that actually that's electric potential energy,
Oh, okay.
which is very similar, but
Mm.
the difference between electric potential energy and just electric potential, well, so like electric potential energy is an energy, right? So it's in units of joules.
Oh, so then electric potentials in volts.
Right. Yeah, exactly. Yeah. And it's K times big Q divided by R. And so the difference between those two is just dividing by the charge or the test charge, right?
Mm.
Okay. And so if that's in joules and you've divided by test charge, then this is going to be in units of joules per coulomb,
Okay.
which is equal to volts. So just remember that volts are just energy divided by charge, or like
Okay.
the amount of work required to move a charge divided by what the magnitude of that charge actually is.
Okay. So,
Yeah, it's
no, so when I had given you a definition, I had given you the definition I wrote down for electric potential energy.
potential energy. Yeah, yeah.
Yeah.
Yeah, so
Okay.
electric potential is just accounting for or discounting what the value of that charge actually is. Because we can say what the electric potential energy is for moving a specific magnitude charge. But if we want the electric potential, that's just any charge can move.
Okay.
And that's the energy it takes to move any charge because we're dividing by the magnitude of that charge itself.
Okay. That makes sense.
Okay, cool.
And that was my one question on what I've worked through in the physics so far.
Okay. All right. Cool. Yeah. Yeah. Then that's a really interesting, pretty decently cool idea. There's actually the person I was working with right before you. The reason it took me a second to get into our meetings because I have meetings booked out all day long today.
Oh,
So,
wow.
yeah, I barely got here in time in order to to jump into that first meeting. I've got like nonstop meetings basically until like 10 p.m. tonight. Um, so let's see. There's a practice. It was just a practice question with the guy that I was just working with before you that
Mm.
actually mattered a lot for like this potential stuff, but I can't find it now because I've still got his stuff up over here, but I don't know. It's not coming up. That's annoying. Whatever. Let's see if it's in the notes. Really, I just wanted to, because it was a really good practice question.
Okay.
So wait, that's not even. Oh, weird. Did I write? I may have put his stuff that we were doing today in the wrong.
No,
So it's
that's
gonna
always
take
the
me
worst.
forever to find. Yeah. Wonder if it was down here. Damn it. It's gonna take me so long to find because I need to, like I'll have to send him the notes. That's so stupid. Oh, wait, here it is. I didn't see the period. Okay, cool. Okay, here. Electric potential. Okay. Yeah, so well, never mind. It's basically what we just talked about, the units of electric potential. So it does talk about batteries, but that's stuff that you haven't done yet. So actually we'll just skip over this. I don't want to,
Okay.
make you do shit you haven't even read or prepared for. That would just be annoying. Um, okay. So you said you don't have any more stuff, any more questions
Nothing
on the
that
physics
I
stuff?
had while reading through.
Okay, let's cover some of the acid-base stuff then, if you don't mind, because that's one of the most important things on this test. Also,
Okay.
the acid-base stuff is hugely hugely important. And so, like, just tell me if you already know all of this and you don't want to, and we can move to something different. But just to reference a few of the
Okay.
things, acid-base. All right, so I'm just gonna give you like as quick as I can or as quick as you want to go through it. My spiel on like teaching some of the acid based stuff, just because there's some ways of thinking about this that I think some professors try to teach and they just don't really get it across.
Mm.
Um, so first and foremost is this idea of like Ka and Kb and all of that stuff. So what is the Ka? What does Ka of an acid actually mean?
The Ka of the acid,
Yeah.
that's a good question. I know, like, if you have a small Ka, you have a weaker acid.
Okay. Yeah.
Like, that's
Smaller Ka
drilled that's
acid.
drilled into me. Um,
Okay. Yeah.
and then if you have, like, a small Kb, it's a weaker base. Um,
Mhm.
is Ka, like, the amount it dissociates? Ka is the amount
It's
it dissociates.
It's got something to do with that for sure. So, like, the bigger the Ka is, the more it's gonna dissociate.
Mm.
But I want you to be able to know exactly what I'm referring or, what the thing is referring to whenever it says Ka. So Ka for an acid, Ka of an acid
You
is
are not.
equivalent to the K. Oh, my bad.
Yeah.
Let's see. Share. Well, was I not sharing my screen that whole time that I was just drawing out all this stuff over here? Oh, I guess I didn't draw it that much. I was just drawing out electric potential and electric potential.
Yeah,
Okay.
no, it's okay.
Ka of an acid. So the of an I just draw my pen. It's so annoying. One second. Okay. That was hard. All right. Ka of an acid is equivalent to the Keq of that acid-base reaction. All right.
Okay.
But that's kind of weird because to say that the Ka is of the acid, that's like the acid is just one of the reactants, right? In that reaction.
Mm.
So the question, but versus like a KEQ is an equilibrium constant for a given reaction, right? So how can you say the Ka of an acid when you don't know what that acid is reacting with? How does that make any sense?
Because you know how much moles it's going to give to the other side of the equation.
Yeah, but you don't even know what the equation really is if you're just saying of that acid, right? Like if I tell you the Ka of HCl, well, if Ka is an equilibrium constant, the Ka of HCl reacting with what?
Okay.
You see what I'm saying? So
Yeah.
there's that, and so the thing that people really kind of don't really account for is that this Ka is the equilibrium constant for this acid, but it's the equilibrium constant. I'm sorry, I'm just going to write this out because this is so important. Equilibrium constant of the acid reacting specifically with water.
Okay.
So anytime you say the Ka of the acid, that's implying that the acid that in question is reacting with water. So we're going to have some generic acid here. Let's just say HA, right?
Mm.
And that HA is always going to be reacting with water because in every acid base reaction, you're going to put your acid into water. Water will always be the solvent. And
Mm.
so every single time you have an acid reacting with water or a base reacting with water, you show what that reaction forms. And so if it's the acid reacting with water, you're always going to form H3O plus and then the conjugate base of that acid,
Mm.
right? So this A negative is always going to be our conjugate base, right? And so for that specific reaction right there, for this specific reaction, we have the Ka of that reaction, right? Ka is just KEQ, right? So you've
Mm.
got products divided by reactants.
Yeah.
So your products are just going to be H3O plus, right? And A negative. That's really messy. And reactants are just HA down here in reactants. Because like you said earlier, water is a liquid. You don't put the liquids and the solids into that
Yeah.
equation. Right. So that is what Ka is for every single acid.
Mm.
Okay. So now let's think about a few specific or okay, wait, just okay. So if an acid is a strong acid, that means that it's going to dissociate more, right?
Yeah.
And so where's your cutoff for if it dissociates more than it doesn't dissociate? What would be your Ka if the acid is strong? Like what's the minimum Ka
Greater
for the
than
acid?
1, right?
Right, exactly, because that means it dissociates more than it doesn't.
Mm.
Right. Okay, cool. So let's think about a few specific instances then. All right. So the classic example of a strong acid is going to be this H3O plus thing, right? So you've got H3O plus is a strong acid. Okay.
Mm.
And so what is the Ka of H3O plus? Well, what's it reacting with?
Water.
Okay. So do you know what the Ka of H3O plus is? Do you have that memorized?
I don't.
Okay. So, well, you can calculate it using this. Or, sorry. Sorry, I've got allergies. I
No
didn't want to
worries.
sneeze directly into the microphone. All right. So what are going to be the products of this reaction right here? H3O plus water.
Um, H2O.
All right. So you've got H2O, right? Because the H3O plus is dissociated plus what?
Mm. Plus H3O plus.
All right. So what is the Ka?
Like, oh, it's 1.
Yeah, exactly, right? Because Ka is just equal to H3O plus divided by H3O plus, right? Which
Mm.
has to be 1. So that's why the Ka of H3O plus is 1.
Mm.
So that tells you that H3O plus is the weakest of the strong acids.
Okay.
Yeah, and so for an acid to be a strong acid, it has to be stronger than H3O plus,
Okay.
which makes sense because if any acid, right, think any acid, your HA appear in this generic reaction that I wrote earlier, HA
Mm.
plus H2O yields H3O plus plus A minus. So that tells you that the acid has to be stronger than that H3O plus. Otherwise, this equation is going to lie on the side of the reactants.
Mm.
Right. Okay. So that's kind of so that's how you can think about strong acids, for instance.
Okay.
All right. So here's another situation where we have, let's think about H2O as our acid now. Okay.
Mm.
All right. So if H2O is our acid, then what's the Ka of H2O?
Well, you could write that out, right? And then you'd be water's.
So H2O has to react with itself here,
Yeah.
right? Okay.
And
Yeah.
so this is like water auto-ionizing.
Yeah. Yeah. Exactly. So you end up with H3O plus OH minus, which
Mm.
is somewhat unlikely, you could say. Right. Okay.
Mm.
So yeah. So the Ka
Is H3O
of
plus times OH.
right. Yeah. So the Ka of water is just your concentration of H3O plus times your concentration of OH minus. Right.
Oh, and then your pKa is 14.
Right. Yeah. Exactly. Which means your Ka is what?
10 to something. 10 to the negative 14.
Yeah. Exactly. And we're going to define that as Kw.
Okay.
Okay, so then, and this is a hugely important equation for acid base stuff. You've got this equation that is Kw is always going to be equal. So this is always true. Kw is always equal to the Ka of the acid present, right?
Plus
Times
times, yeah.
yeah, times the Kb of that acid's conjugate base.
Mm.
Okay, so for water specifically, so if water is your acid, right?
Mm-hmm.
That means that, well, we just said that it's 10 to the minus 14, right?
Yeah.
Okay. So what is the conjugate base of water?
Hydroxide.
Okay. Right. So what is the Kb of hydroxide? Well, we said Kw is 10 to the minus 14, right? Because
Yeah.
Kw is the Ka of water.
Yeah.
And so if water is our acid, then we just have 10 to the minus 14 is equal to the Ka of water, which is 10 to the minus 14. So that means that Kb of hydroxide necessarily has to be 1, right?
Yeah.
Yeah. So Kb of OH minus must equal 1.
Okay.
All right. So that is by definition, just like, so hydroxide is equivalent to H3O plus just on the base side of things. Right?
Okay.
Yeah. And you can also write out the base reaction because Kb is just like Ka. Kb is the equilibrium constant of any base reacting with water.
Mm.
Okay. So you can use OH minus. I don't know why I switched over. Maybe go back. Okay. There. All right. You can use OH minus and make that react with water. And so what would be that product?
H2O plus
Right.
OH.
Right. And so what's the Kb of that reaction?
OH over OH, which is 1.
Right. Yeah. Yeah. And so that's just that proof again. All right. And so you can do this for any acid-base reaction, period. All right. So and that allows you to do a lot of stuff. So for instance, let's think about hydrofluoric acid. All right. Hydrofluoric acid has Ka of 10 to the negative 6. All right.
Mm.
So the question is going to be calculate the Kb. We say, like, what is Kb of F minus?
Mm.
All right. So what is that?
I'm writing it out.
Okay. Yeah. Yeah. Go ahead. I'm just trying to go fast because I know you're keeping up really well. So I just don't want to make it boring.
Yeah, no, it's okay. Ka of HF is okay. And then KW KA times KB.
I just set my pin down. Oh, there it
14,
is.
it'd be 10 to the negative 14 divided by 10 to the negative 6.
Right.
Yeah, so that's just 14 divided by 6 in the logarithmic scale. Well,
Okay.
no. Is it? No. Maybe. I don't know.
So anytime you have division or anytime you have multiplication
It's
of
addition
two
because
exponents, right.
it's 14, and then that's why I said addition earlier because I typically hate scientific notation.
Right. Yeah. 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 Okay.
So
Yeah.
then it would be 14 minus 6, which
Mhm.
is 8, which is 10 to the negative 8, right?
Yeah. Yeah. Exactly. Perfect. So KB of F minus equals 10 to the negative 8. Right. So is F minus a strong base or a weak base?
It is a weak uh weak base.
Yeah. Perfect. Because it's less than 1.
Mm.
Okay, cool. Yeah, exactly. And so a lot of these are going to be just like that. So for instance, like let's calculate okay, now say pKa, let's figure out pKa of H2SO4. All right. And
Mm.
I'll tell you that let's see. Okay, and that the Kb when Kb of HSO4 minus equals 10 to the negative 22.
Okay. Oh, you're wanting me to find the pKa of
Yeah.
H2OSO4
Yeah.
given. Okay.
Yeah.
So, well, I'm gonna write out my reaction because that's always nice to have something to look at.
Yeah, for sure. Yeah.
Okay. And then uh okay. Um so I'll so you could just do so you gave me the KB this time and you're wanting the pKa.
Yeah. Yeah. I just threw another step in
Okay.
basically.
Uh is it just not I know this is wrong, but it's not -8 because that's not right.
It's not
No.
-8, right?
Yeah.
Because okay. Oh wait, I'm sorry. You're saying the answer to the whole thing?
Yeah.
Okay, yeah,
Is it
that is true. Yeah. Yeah,
okay.
it is -8. Yes. Yeah, yeah,
Okay.
yeah.
Okay. I
I
was
thought you
like,
were
wait.
saying okay, yeah, yeah, because that's because you know how to do it. So it's 10 to the minus 14, right? And you said 10 to the minus 14. Well, 10 to the minus 14, 10 to the negative 22. So you knew that this had to be 10 to the 8, right?
Yeah.
And then so pKa equals negative log of Ka. And so negative log of 10 to the 8 equals -8. Yeah, perfect. Okay. You just did it really fast. So
Is
I
it
thought you were gonna do what?
is it wrong that I convert everything to the logarithmic scale?
What do you mean by to the
Like the
logarithmic scale?
pKa's? That's where those numbers come from is the log. They
Yeah.
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 So like whenever you give me like I don't understand why I hate scientific notation so much, but I hate
Oh,
it.
okay.
So I just instantly convert everything to the logarithmic scale.
That's fine with me. You can. If I were you, I would get comfortable with scientific notation because that's going to be really helpful for this test because
Okay.
they use the shit out of scientific notation.
I know. I just
Yeah.
hate it because it's just more writing to do.
Oh yeah, yeah. So I almost never write the coefficients in scientific notation because then like 10 to the something.
Mm,
It's still, but I get it. You still have to write the 10 whatever.
yeah.
So you can do whatever you want if that's how it works for you. It seems to be working. So I think that's totally fine. Just
Okay.
recognize, just as long as you don't forget the negative, which you didn't there. So yeah, it works for me. I think it sounds
Okay,
like a
cool.
good idea. Yeah. All right, cool. So yeah, so that's some acid based stuff. um, so then let me think. How can I convey this? Okay. So the another thing in the acid base world to be aware of is the buffer equation. You know what I'm talking about?
Yes. I wrote it down. Or at least I thought I did.
All right. Yeah, I can.
I guess I
So
didn't.
it's
I might have erased it.
yeah, so it's the pH of the solution is equal to the pKa,
Oh, you mean the Arrhenius equation?
or this is the Henderson-Hasselbalch equation.
Or that yeah, that's the pH is equal to the pKa plus the molarity of the conjugate acid over the original acid.
Okay, yeah, 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 or conjugate base of the original acid, but
Yeah.
yeah.
Okay,
Yeah,
cool.
so that's gonna be your buffer equation, and you're gonna use that a whole bunch, but just know that that's present. You could also there's another version of it that is POH
Mm,
is equal to the PKB plus log of the like what would you say like HB divided by B negative.
yeah.
Yeah. So that's the other one. But just as long as you're aware that that's a thing.
Mm,
um okay, so how about then this reaction? So whenever your tissues create CO2, right? You need to transport that CO2 back out into the atmosphere, right? Otherwise you
mm,
get carbon dioxide poisoning and you die. So you have to have a way of doing that. Unfortunately, CO2 is a non-polar molecule. It has two polar bonds in it, but the whole molecule is just linear and its two polar bonds cancel each other out. And so this molecule is not water soluble for that
mm,
reason. And it has no hydrogen bonds. So, all right. So CO2, not good at moving around in the blood because the blood is a water based solution, right?
mm.
So you have to have a way of moving CO2 in the blood. So, how does that get done? Well, you
But
convert it.
yeah.
Oh, go ahead.
So you would do like CO2,
Hmm.
right?
Yeah.
Plus water, right?
Yeah. Yeah. Perfect. So you've got CO2 plus H2O.
And
And
then you
that
get
is a
HCO2 plus the hydronium ion.
It's actually so this is H2.
Oh,
So this is a totally different reaction. This is an enzymatically catalyzed reaction that
yeah,
turns it
okay.
into H2CO3, right? So then your H2CO3 will that plus water is an acid base reaction that
Mm,
forms HCO3 minus plus hydronium. All right.
yes.
Okay. So you've got that reaction and you know that the pH of blood is what?
7.
7.4.
Okay, cool.
pH of blood is 7.4. All right. So then, and so now let's figure out. I'm trying to think which direction do we want to do this. Okay. So I can tell you that the pKa, because they would give you pKa on the test, right? Unless they were having you
Mm,
solve for it. But pKa of H2CO3 is like 6.3. Okay. So what's the ratio? So the question would be what is the ratio of HCO3 minus 2 H2CO3 at pH equals 7.4.
Okay. Give me 1 second. This is the acid, that's the base. This is the conjugate acid, that's the conjugate base. And then what is the ratio? So then that's where the Arrhenius equation comes in.
So this is called the Henderson-Hasselbalch equation.
Oh, I always mix them up. I did
Yeah,
this even in Gen Chem. I'm
I
gonna
mean,
write that
yeah,
down.
and it really doesn't matter if they're not gonna have you name the equation or anything. I just wanted
Okay,
to let you know.
thank you. I don't know why, but I keep on just even when I was reading it, I would like read over the name and then I would say Arrhenius.
Yeah. So this is it doesn't matter the name, but I just wanted to tell you.
Okay, thank
Okay.
you.
Yeah, no problem.
Right. And then so then this is so I'm gonna figure out my pOH first. So you just 14 minus 6.3. That's 3. So then the pOH is 7.7, and then no, that's wrong. I figured out the pKb.
Oh, I see what you're saying. Yeah.
And then I have to know my pOH now, which I can do because I know how to do that.
So why are you doing pOH?
Because you can just because you're asking for the ratio of HCO3, which is your conjugate. Oh, I see my mistake now. So you could just do the pH, right?
Yeah.
So then that makes things simpler.
Yeah, much simpler. Yeah.
And then my pH is 7.4.
Mhm.
And then that's 1.1 is equal to the log of our ratio that we want to find. And then you want
Right.
to take, I don't know how to estimate this, but you could take like the log of both sides. No, how do you do this again?
Well, you could just say, that it's like 1, right? Because,
Yeah,
1.1 is basically 1. 1 equals the log of something. You say 1
yeah,
equals log of x. Well, what is the thing whose log equals 1?
0. Do I no? I'm
Remember the
having a
log of
day
something.
today.
Yeah,
I'm
oh no,
having
you're good. This is not super simple. I mean, well, it's simple if you know exactly how to do it, but so the log of something is just the power 10 needs to be raised to in order to get that thing, right?
yeah, so it's 0.
Well, so if the log of something is 1, then that means that 10 needs to be raised to the power of 1 in order to get this thing.
Okay.
And so it's just 10,
Okay.
right? So here x equals 10, right? Because log, because if you put it in, you can check your work by just going backwards. So you say log of 10 is equal to 1, right?
Yeah, okay.
Yeah. So you know that ratio then is 10. And so
Yeah,
that's your
okay.
answer. Yeah.
Okay, cool.
And so that means that it's mostly dissociated. It's 10 to 1,
Mhm.
dissociated versus associated at
Yeah.
physiologic pH. Yeah.
Okay.
And so that is a buffer,
Okay.
right? Your H2CO3 to HCO3 negative, that's a
Mhm.
buffer system. And so that is the way that we're able to maintain our physiologic pH within like a really tight range.
Yeah, okay.
Yeah. And so if our physiological pH gets too low, then what we do is we increase our respiratory rate so that we're pulling off carbon dioxide, right? Which
Mm,
means that we're taking this and transferring it to carbon dioxide more, which means we have less acid present,
okay.
right?
Okay, yeah.
Yeah, and so that's how we raise our pH is just by increasing respiratory rate. Damn it. Whatever. Okay. Oh, does that make sense?
Yeah, it does.
Okay. So that's
I'm
just
just
like a
more
pretty.
astonished that I can't do simple math today.
Oh no, you're fine. Don't worry about that. That doesn't matter at all. So yeah, so that's pretty much like almost all of the acid basis stuff right there.
Okay,
Like we
cool.
basically just did all acid base right there.
Are like do you know like I don't know if I was taught it was called like rice tables? Are those on the MCAT?
You can use those if you want, or ice tables. I've heard them
Yeah.
called both things. I mean, it's you can use them if you want to. I don't. I kind of just like don't care what the way that you solve that because it's just like your initial, your change in your end or final or whatever you want to call it
Yeah.
situation. I'm trying to think of a good example where people use those. I just never use them, so I don't have a
No,
great way
no,
of
it's okay. I
thinking
don't
through it that way.
I don't want to use them, so we can skip it.
Okay, yeah, so don't. Yeah, if you don't want
Yeah.
to, it's really those are really good for helping people who aren't good at setting up problems for themselves set up problems.
Mhm.
But I don't see that being an issue for you, so I really don't care. That's
Okay.
like that's something that if you were somebody who I kept seeing was having trouble with math, which you're not,
Which
like
I
you
clearly
obviously
am.
no, you're not. Then I would teach you it that way, but you're good at math, so I don't need to do that. I mean, they're kind of useful to have in your back pocket if you want, but it's up to you.
Yeah, okay.
So, all right. So that was acid based stuff. So that was really good. I'm trying to think of what we should do
Oh,
now.
here's a
Oh,
question.
go, yeah, go ahead.
Will we be shown titration curves on the MCAT and be asked to
Yeah,
identify points?
yeah. You want to do that?
Yeah.
Okay, cool. Yeah. So titration curves. There's two different ways of doing it. You can do but basically the idea is that you're gonna have a graph where you have like pH or you could have POH, either one, but let's do pH for now.
Mm,
And you've got either an acid or a base that's unidentified or something. So we'll just think of it like, all right, let's just think of a system where we have, all right, so let's say we start out with a bunch of acid in our system,
mm,
and we're going to titrate pH. We're going to titrate OH, right? So we're going to add little drops of OH, or it will say NaOH added. Okay. So we got our
mm,
pH and we've got NaOH added. And obviously, like the more NaOH we add, the higher our pH is going to be. So we got pH of 14, pH of 0. We put like 7 somewhere here in the middle. So I'm just trying to define this that way we can have like decent bounds on this,
mhm.
just to see where it is at all times. 10 and maybe like, I don't know, 9. That was terrible. Okay. This is 11 there. All right. Just so we can know like roughly.
Yeah.
All right. So now we just have to think, all right, as we add OH, what is going to happen to this thing? So, well,
The
initially our pH is let's say our pH is 0 initially. Okay.
mm,
So as you add OH, what's the first drop of OH actually going to react with?
the water.
Right. Yeah. Or it's going to, so yeah, because you've got some acid. Let's just say for right now, let's do a simple one. We've got a bunch of HCl in solution. Okay.
Mm,
So if we put our HCl in solution, that HCl is all immediately going to react with water, right, to form H3O plus and Cl minus, right?
mm,
So we've got really concentrated solution that is almost entirely this,
yeah.
right? Because HCl dissolves really, really well. Okay. So there's no HCl in solution right now because it's all dissociated and
Yeah.
formed H3O plus. So as soon as you add OH, your first OH molecule that you add is just gonna, it's gonna be OH plus H3O plus to form H2O,
Mm,
right? Or two molecules. of H2O. Okay.
Mm.
So is that going to increase or decrease? How is that going to affect your pH?
It's gonna increase well, it's gonna start raising
Yeah.
your pH, but it's not
Right,
gonna
exactly.
shoot it up.
Because what all pH should honestly be called pH3O plus, right? You know
Yeah.
what I'm saying? Yeah, which is just negative log of the concentration of H3O plus. Wow, this thing's bugging out today. You know, like it's making my drawing's like jumping around as I'm drawing. It's weird. Okay,
Oh.
so basically that's saying that at the very beginning, every time we throw OH in there, every single initial OH, like every single mole of OH or drop of OH or molecule of OH is going to react with a molecule of H3O plus, right?
Mm.
So initially we have this rapid rise in pH because you can think of it as like 1 mole of H3O plus is going to react with 1 mole of OH every time we put one in,
Mm.
right? Okay. Actually, HCl is a terrible example. So sorry, let me fix this. Okay, let's just use the same acid-base system that we had before. All right.
Mm.
Because you don't normally want to do it with a strong acid, like a strong acid and a strong base, because the pH of or the pKa of HCl is actually really low.
Okay.
Yeah. So okay. So it's going to be a weak acid that you have in there already. All right. So that's going to happen in a 1-to-1 ratio until eventually as we get closer to the pKa of our acid, and remember we said the pKa of this acid is what, like I think I said it was like 6.3.
Sounds right.
Okay. So as we get closer to the pKa of the acid, we're gonna start getting into a situation where now our reaction is shifting over here, right, to where we actually have some of this in solution.
Mm.
Right. Let me think. Am I fucking this up? Okay. I have to think through. Oh no, that's good. Okay, we're good. We're good. Sorry about that. I had to brain freeze for a second. So initially all we're doing is pulling H3O plus off of, or we're pulling the proton off of H3O plus, right?
Mm.
As we increase, our pH continues increasing because our pH is going to increase relatively quickly up front because every single molecule of OH that we put in again is pulling 1 molecule of H3O plus out. And as we get close to the pKa of our acid, now we're going to start deprotonating some of these also, right? Because every single one of these is protonated at really low pH. Okay.
Yeah.
Okay. So rather than pulling all of the H3O plus, all of our protons off of H3O plus, now we're going to start also pulling some of them off of this acid, right?
Yeah.
Okay. So now every molecule of OH we put in doesn't get rid of a molecule of H3O plus. Some of them still do, but some of them get rid of molecules of our acid that we have. See what I'm saying?
Yeah.
So now you get less of a pH change. I keep wanting to change the slope of this. Now you get less of a pH change per change in OH, per OH added. Until eventually you get, once you get right on the pKa of your acid, now every single molecule of OH you put in is deprotonating acid rather than deprotonating H3O plus.
Okay.
So there's this flat period where you're only deprotonating your acid and not deprotonating H3O plus. Therefore, you're not changing the pH at all per OH added.
Okay.
But then once you start to run out of acid to deprotonate, then you're left with only being able to deprotonate H3O plus again. And so your pH starts to rise rapidly again.
Okay.
So there's this flat period. So this flat period exists. The flat period exists where, I'll just say like flat near pKa of acid in solution. See what I'm saying?
Yeah. Quick
Okay.
question.
Yeah, go ahead. Sorry.
Isn't there like 2 flat periods because it's a diprotic acid?
Well, this is okay. Yeah, yes. Okay, yeah, that's true. You're right. But it would be up
Okay.
higher, right? This
I wanted
part
to
would
make
be
sure
up
I
higher.
wasn't going crazy.
Yeah, it would look like that. You're right, because
Okay.
this would be the HCO whatever minus.
Yeah, okay.
So it would be a lot. And I probably drew it too low there, actually. It'd probably be up more. So it'd probably be like up here more. But
Okay.
yeah.
Okay,
The
cool.
reason
I
I
was
picked
like
HCl initially is because I didn't want to do a diprotic acid initially. And then I kind of forgot about that whenever I switched over. Sorry, that was like the most unsmooth explanation I've ever had of
No,
this. I
it's
just
okay.
kept having to backtrack.
Okay, that makes sense.
And I'm definitely failing in drawing this curve.
Just blame it
But
on the pen. Blame it on the stylus. You gotta replace the
this
nib.
thing actually is having some issues right now, but I think my computer also hasn't been restarted or anything in a bit, so I might just need to restart. Um, okay, so let's do another example of this just so I can make sure that that it's clear because that was not very good. All right, so this time let's do it the other way around this time.
Mhm.
Well, not like that. What is that? There's a bug in OneNote. This is legitimately not my fault. There's a bug in OneNote where sometimes when you draw out a coordinate plane like that, it will make it inverse of the way that you meant to do it. It's really weird. Okay, here we go. All right. So this time we're going to say that we start out with a base in there. Okay. So
Mhm.
what's a base that we could put in? So let's say that we just start out. Damn, why can't I think of one? Okay. So we just have, let's say we have like, I don't know, NH3. Okay. And so now we're going to be titrating with HCl.
Okay.
All right. So our pH is going to start off up here. All right.
Mhm.
And 0. Okay. So now as we add HCl, what's going to happen to the pH?
It's gonna like flip the other way around. Like your curve's gonna look the other way.
Yeah. So it's going to start going down, right? Because
Yeah.
every time we add HCl, we're going to protonate what? What are we protonating?
Uh, the hydroxide ions initially,
Yeah,
right?
exactly. Perfect. Yeah, yeah. So as we add that, we're going to start protonating hydroxide ions, which is going to drop our pH really
Mhm.
quickly, right? Okay. So yeah, so protonating hydroxide ions, then we continue going down. Eventually, let's just say I don't know what the pKb of NH3 is, but let's just say pKb equals I don't know 8.5 or something. Yeah, for the sake of this. So as we
Yeah.
get close to 8.5, then what happens or what starts
It
happening?
starts to flatten out
Okay. Why does it start flattening out?
because it starts protonating the NH3.
Right, perfect. Yeah. So now you're not changing your concentration of hydrogen ions in solution anymore because you're protonating only NH3. Yeah, exactly. So it flattens out, but then you run out of NH3 and so it drops down again.
Yeah.
All right. So and then the only other thing left to talk to that I didn't put in this graph up here is to mention like what this point is actually called. The flattest point.
The equivalence point.
Flat, yeah. So this is actually not the equivalence point. So
Oh,
it's the 1/2 equivalence point.
okay.
Yeah. So the 1/2 equivalence point is where you've deprotonated or you've protonated, depending if you're talking about acid or base,
Okay.
exactly half of your species in solution.
Okay.
Whereas the equivalence point,
Is up. It's a yeah.
where your equivalence point is where you've protonated all of it.
Okay. Is the equivalence point the same thing as your end point?
Um,
Because the Kaplan, unless I
Let me
wrote
look
it
it up.
down wrong, the Kaplan book calls what you labeled the equivalence point the end point, and where you marked the 1/2 EQ point as the EQ point. But
Does it really?
I might have just written it down wrong.
I could have it mixed up. Also, I want to look at that because I just want to make sure.
Well, because I remember like when I took Gen Chem, they taught it like, or they showed it the way you had it, but
Oh, okay. So there could be an error in the capital book also. I think, or actually no, I think you wrote it down wrong because I'm looking at it in my book right
okay.
here.
Yeah.
And there could be an error in the online version of the book also.
Yeah. Look, uh, I want to share what I see.
Yeah, go for it. Oh yeah, I might have to stop.
Oh, yes. Cool. See, this is called the EQ point, and then this is called the endpoint.
Oh, weird. Oh, I see. Wait, what the hell?
Is it because well, even if like the other ones, they label this the equivalence point.
Yeah, so the equivalence point is the steepest part of the graph for sure.
Okay.
See, and the 1/2 equivalence point is the flattest part of the graph.
Okay, so that's right. Oh,
Mhm.
okay. Okay. I guess that makes sense. I just drew it wrong on my own graphs because I didn't
Okay,
understand what it
yeah,
was
so yeah,
showing.
that makes sense. Yeah, so it's just the equivalence point, because if you think about it, it makes sense that the equivalence point is the steepest part, because that's the point where you're completely out of species in solution, and so, you're just, like, straight up changing pH per everything
Mm.
added. So, yeah, so then just trying to think of a way of doing that with, like, amino acids or something. I mean, you definitely can actually, yeah, amino acids are commonly done on this. So we could think about, like, for instance, if you have, trying to think of an amino acid. Let's just say like glycine. Okay. So you've got glycine, you've got your H, what is it, H3 in this. So positive charge there, carbon. And then obviously you've got two hydrogens here. And then COOH, right? Or, that can be negatively charged, but the positively charged version of glycine looks like that.
Mm.
So let's say we've got glycine at really, really high or really low pH initially. All right. So then we're going to be adding NaOH added. All right. pH 0 and 14. So we're starting out at pH 0. So what's going to happen initially as we add NaOH? So at pH 0, the molecule looks like this, right? It's positively charged.
Mm.
Okay. So what happens initially as we add NaOH?
Um, the oxygen goes to the positive charge.
Uh
Or wait, can you repeat what was asked? I
yeah. So
spaced
what
out for a
happens
second.
initially as we add NaOH to this to glycine at see how it's protonated everywhere right now?
Yeah.
Like, it's protonated on both carboxy
Yeah.
and N-terminus. So
Yeah,
what
okay.
happens initially as we start adding NaOH to the solution at pH 0?
It starts bringing the pH up
Yeah,
away
yeah,
from
because
0.
it's deprotonating hydronium
Yeah.
first, right? Yeah.
Yeah.
Okay. So pH will initially rise rapidly, but then what? Like, say, I don't know, maybe this is 3, and we'll say that our pKa of this pKa equals 3 of this,
Okay,
and
and
then
so it starts flattening out then because it starts like starting to the deprotonate the glycine.
yeah, exactly. It starts to deprotonate the carboxy end, right?
Mm.
Okay. And then so as it does that, then eventually it starts to go up again once we run out of carboxy end. And then it climbs again for a while until we get up near the pH of the N terminus end, and then it flattens out again and then climbs more. Right.
Mm.
So then you would have like so this would be your equivalence point. So this could be like your carboxy equivalence point. And then this over here would be, like your amino equivalence point.
Mm.
And then you'd have obviously your two, you could say these are your 2 1/2 equivalence points.
Really?
Yeah. And then you can tell. So, how would you tell how much amino acid you have in solution? Because you can also tell that just by just using this.
How much amino acid you have in solution?
Yeah. Yeah. Because you're
Um,
measuring moles of NaOH added, right?
mhm.
So, how would you know?
At the half equivalence points, you could know how much Na you've added, and then that would tell you how much. Um,
Yeah.
yeah.
Okay. Yeah. Yeah. You could either look at your 1/2 equivalence point and just know that you've got twice as much amino acid in solution as Na that you've added, right?
Mhm.
So we'll say that this is like, let's say we added 3 moles right there, right? Or you
Mhm.
could just look at your equivalence point and know that now you've deprotonated all of one of the ends of the amino
Okay.
acids. So yeah, so with your equivalent, oops, what just happened? So with your equivalence point being at 6, that means that you have 6 moles of, since I use glycine in this solution.
Mhm.
Okay, cool. And that's just some of the stuff that they do with that.
Okay,
So
cool.
yeah, and that's pretty much it, I think, for the titration curves.
Awesome, because I don't like
Titrations used to give me a lot of trouble whenever I was in undergrad.
titrations.
Yeah, it's just kind of hard to keep everything in your head. But if you think about it, in this way, where you're thinking like, okay, what's happening whenever I'm
Mm.
to each molecule of NaOH that I add or to HCl that I add, then it
Yeah.
kind of makes a little bit more sense, I think,
Yeah, it
because
does.
the pH is only changing as you deprotonate H3O plus.
Yeah. Okay.
Yeah.
Okay,
All right.
cool.
Cool. And so that's why the buffer system does the best near the pKa of the acid that's in the buffer system, because that's where it's able to flatten this curve out. And so
Mhm.
by buffer, it just means that the pH doesn't change as you add base or as you add acid. And so the buffering region is this flat region,
Okay.
right? Because it only is a good buffer in that region. Outside of that region, it's not helpful.
Okay.
Yeah. And so normally they refer to, I just draw like that. This normally they refer to this buffer as the buffer region, and that is just like conventionally referred to as being plus or minus 1 pH of the pKa. So it's within, like it's the pH being within plus or minus 1 of that
Yeah.
pKa. Yeah.
Okay.
So like for the carbonic acid system that we looked at up here,
Yeah.
right, where pKa was 6.3, then the buffer region would be between 5.3 and 7.3.
Okay.
Yeah. So why would but blood pH is 7.4, right?
Mm.
So why is the blood pH outside the buffer region of that carbonic acid system? Why would we do that?
Because you want your blood slightly acidic.
Well, not because you want it slightly acidic, because you want
You want it.
protection from it being slightly acidic.
Yeah.
Yeah.
There we
Yeah,
go.
because the buffer region exists. Yeah, the buffer region exists beneath. But why do you care more about protecting from it being slightly acidic? Because too basic will kill you just like too acidic will.
Is it because it's easier to um keep something? It's easier to keep. It's easier to keep. I can't put it in words. It's easier to keep something from becoming too acidic. Is
Well,
that right?
then we would want, yeah, I think you mean that it's easier to keep it from becoming too basic, or I don't
Yes.
know. Yeah.
Yeah.
Well, not like objectively speaking, but within the body, yes, because the like if we let the process just happen as it's going to, like if we stopped breathing, the trend is that we're going to become more acidic. We don't have
Mhm.
anything going on in the body that's going to make the blood too alkaline just from like just passively, right? But metabolism produces CO2, which produces more acid.
Mm.
And so our buffer system accounts for things getting too acidic because there's not really a circumstance where we're going to become too basic, short of like intentionally hyperventilating.
Yeah.
So yeah, yeah. So that's why. But yeah, so your intuition, I can tell that your intuition was correct on that because you were
Okay.
thinking, yeah, you were thinking right. Nice. Okay, cool. Let's see anything else. So we covered that. We've really honestly covered everything that I meant to cover today. So um yeah, I don't really have any other problems or
Okay,
anything off the
cool.
top of my
Well,
head.
that makes me feel good that I
Yeah.
prepared enough.
Yeah. Oh yeah, you crushed all of this. You've been doing really well. Uh and so we're meeting our next meeting will be a week from now, right?
Yes.
Okay, cool.
Um,
So yeah. So
oh, before while you're on the call,
oh yeah,
where
yeah.
is the syllabus uploaded?
I looked and it didn't sync. So I just need to make it sync up. So
Okay,
I'll do it.
cool. And then our last video files also didn't sync up.
Oh really? I
Yeah.
might have a syncing issue on my OneDrive. Where's the oh there it is. Oh yeah, I do. I do have a syncing issue. So none of my shit's syncing. Oh, my bad on that. I'll
No
fix
worries.
that. I've got another meeting immediately. I'll try to fix the in between meetings, just depending on how quickly, I'll try to fix it before I start my next meeting. That way you can have it.
Okay.
But if I don't have time to do it, then I will definitely fix it by like I'm done meeting with people at like 9 p.m. tonight or 10 p.m. Either 9 or 10. And so I'll fix it after that at the very
Okay.
latest. Yeah, sorry about that.
No worries.
That's frustrating when shit doesn't work.
And
But
then
for I can go ahead and just show you what you
yeah, so I can write it down. I
yeah.
keep on forgetting to write it down. I'm just like,
Where did I put the thing? Oh well, this is not what the looks like, but whatever. This will work. So
okay.
yeah, so this will be next time is this stuff.
Day 4, 11, 12 for chemistry, and then ooh, we're in biology.
Yeah. Yeah, because that's it for the chemistry book.
Oh,
Yeah.
all of Gen Chem taught in 3 sessions.
Yeah. We crushed through the Gen Chem because that chapter 12 is really important. And so this stuff, this day 4 stuff, see how we go kind of out of order in biology?
Yeah.
It's because that is extremely relevant to electrochemistry. And so just know that this electrochemistry stuff is going to be the theme of everything we do here on day 4 specifically. And like that's why we're doing nervous system with
Mhm.
electrochemistry because those two go together, right? Because electrochemistry and nervous system, those are the same subject.
I hope I absolutely crushed the nervous system as a neuro major.
Okay, yeah. So I was a neuro major also. Yeah,
I hope
it's not that bad as compared to like whatever neuro classes you took. It's really not too bad.
okay.
Like parts of action potential basically is about
Oh,
it.
okay.
And then skeletal muscle is basically the same thing as the nervous system. It's just like a bigger neuron. That's what a skeletal
Mm.
muscle is. And so that's why I threw that in with that.
Okay,
But
cool.
just know that electrochemistry is the, and I say the single most tested thing on the MCAT.
Okay.
So that's why we rush through Gen Chem so fast is just so we can do this.
Okay.
Yeah.
Alrighty. Well, thank you. I actually wrote down the chapters this time.
Okay,
So I
cool.
won't be
Yeah.
texting you the day of.
Oh yeah, and you'll have it in the folder also. I'll just drop it like in the main folder and then you can put it wherever you want
Okay,
in there.
thank you. That sounds good.
Yeah, no problem. And hopefully all that stuff will sync up. Let me know if it by like tonight or by the next time you look at it, that hasn't synced up, and I'll just email it all to you. But it should sync up after I fix it. So
Okay,
sorry about that.
alrighty.
It's
Thank you.
probably because I threw the computer in my bag and left before the
Yeah.
OneDrive had time to sync. I just didn't look at it. So
Okay.
yeah.
No worries. Alrighty. Thank you.
Yeah, no problem. I will talk to you on Thursday or sooner. Let me know if you have any questions.
Okay, awesome. Thank you. Bye bye.
Yep. See you later.